Good morning. Let's start today's session. So this is the group photograph. We'll do some picture editing, and we will share this final version later on with all the participants. So we have a special session about 50 years of ASI, and we have three interesting talks, primarily about the observational facilities in different wavelengths from ground and space platform. I would like to point out that probably we have not been able to cover the other aspects also, theoretical and other avenues of development. We'll try to incorporate that. So it's my pleasure to chair this session. It's a bit unusual. The chair is giving a talk, but I just want to wrap up a little bit of what activities we have been doing and we are planning over this year. So there has been a committee appointed to plan and execute the celebration of 50 years of ASI. These are the members of the committee. A tentative budget has been given by the executive committee. I'd like to point out that we expect year-long activities. So we have started, and we will actually have the final say on the next ASI annual meeting. So we expect the entire community to work with us for the entire year so that we can complete some of the tasks which we have planned. But again, this task also we would like to improve and extend as we move on. So this element actually was mentioned, and we are very proud to be able to take up this step. You will hear a small little movie about this particular series. Before I play the movie, I would also like to point out that I am also one of the recipients of Srini's lecture way back in 1990 in the JAP program. That time, Srini used to teach survey of astronomy. It used to be named differently. And it was quite amazing. I'd never had any exposure to astronomy. I am actually accidentally in astrophysics because I just came for the interview and I was selected in the astrophysics and not in the physics. That's a reality. And in ISC physics department. But in fact, IIA faculties were sitting in that interview and they offered us. I was in the waiting list of the JAF. Same with Annapurni and other friend of mine sitting here, Ishwar. We all started our journey in 90, and we are all privileged to have Srini's lecture as our first exposure to astronomy. I chose solar physics, but I was also inclined to do neutron star physics simply because of Srini's lecture, but I was already taken up by IA, so I didn't have the fortune to work with Srini for my career, I would say. So without further delay, let me play this small little clip which has been prepared.
Sir, no audio from the video.
My name is Dipankar, currently a professor at the Inter-University Center for Astronomy and Astrophysics in Pune, India.
I am Sushan Konar, a theoretical astrophysicist.
I am Edward van den Heuvel, Professor of Astrophysics at the University of Amsterdam in the Netherlands.
Professor G. Srinivasan, Srini to his friends and colleagues, is a leading luminary of compact star research in India. After an early career in condensed matter physics, Srini joined the Raman Research Institute in 1976 and began working in the area of astrophysics.
It was his lectures delivered in a summer school nearly 40 years ago that inspired me to take up astrophysics as a career. I joined the PhD program later that year and ended up working with him as my PhD supervisor.
Professor Srinivasan also is one of the most outstanding and inspiring teachers that I have known in my life.
We are very excited about the upcoming lecture series by Professor G. Srinivasan as part of the Golden Jubilee celebration of the Astronomical Society of India. This series, intended for the undergraduate and postgraduate students with a serious interest in astronomy and astrophysics, is unique in its scope and structure.
My name is Srinivasan. Welcome to this series of lectures in which we shall survey astronomy and astrophysics. Some years ago, NASA launched a satellite to probe the corona of the sun. It was named after the great astrophysicist Eugene Parker, who passed away just a few days ago. The giant 6.5 meter James Webb Space Telescope has been launched, parked safely in its final parking place, and has been deployed. Right now, tests are going on of the alignment of the mirrors. In the next couple of months, it will take its first images.
Through the years, I have always admired his passion towards teaching and lecturing. I am sure that this will be a fabulous and long-lasting resource. Many thanks to the Astronomical Society of India for organizing this. So viewers, be prepared for a treat.
So stay tuned for this fantastic series which we are expecting, and the next generation will also be benefited as we have. There are a few other activities we have planned already, and some more are in the pipeline. So this is about the capacity building workshop for early career researchers. This will be led by Poonam and her colleagues here as written. So we have been discussing about, writing observing proposals, water plagiarism. Some of the younger students are actually not exposed to these areas. We have been, also hearing about it, how to give good talks, skills of scientific and popular writing. There were questions yesterday about how to write a popular article. Then we would also like to have very specific sessions for career paths in astronomy, astrophysics, or physics and related physics. Also alternative career paths after the PhD program. This is becoming a very important issue because we are taking more number of students across different institutions. So it's very important to think about their progression in the career as well. We have also, already arranging a special session tomorrow, and we request the students particularly to participate in that program and see how the academia and industry partnership is actually growing. And you will know what kind of skill sets the industry is looking for, for their recruits. Then a big question is availability of the data and softwares and online resources such as Stopcat, Simbad, Aladdin, virtual observatories. You heard Ajit talking about the virtual observatory efforts which he has taken many years back. Incidentally, after Ajit's talk, I also wanted to point out, this is part of the 50-year celebration, that under the leadership of Ajit, he didn't mention it because he was the president, many new initiatives was taken. And the wish list, what he has given, is probably our, big resource for the next 10 years as well. So we were talking about, our activities with the next 3 years of this new executive committee. So I was just telling Anupama, I have already my agenda points ready for all the future meetings. Sorry, I think this is a mismatch of the Mac and the and the Linux and the software here. So what I was talking about, the history celebration and documenting the history of ASI. Anupama pointed out in her opening address, and you heard yesterday as well. We have only this document, 10-year book of Astronomical Society of India. This is 73 to 82 period, and subsequently we don't find actually a proper book. So this is a big exercise which Anupama and Neeraj is going to take initiative and lead on that. We're collecting the archival material. We'll be talking to many senior scientists through online and offline meetings, and we would hope to get a good book ready in the next ASI meeting. So that's one exercise we are going to take. Again, I'm sorry about this mismatch of the Mac and Windows. I should have tested this. So what I wanted to also talk about is about the education approach. So I think the students also need to participate. I'm sorry, the slide is completely got messed up here. Just let me say it in words. The point is, there are two components. One is the formal education and the non-formal education, and at different levels. So there are undergraduate, there are postgraduates, and the PhD students. So we have to work closely with the student community also. So we'll try to have students at ASI 50. We will probably bring it with the YAM link. I will be talking about very briefly about Young Astronomers Meet. We'd definitely like to revive that. And 80 students have already volunteered for that. I'm just getting in touch with the Ayuka team, who has been looking after YAM for many years. So hopefully we'll be having a YAM within 3 to 4 months. So that's also will be part of our ASI 50 celebration. Engaging with synergetic organizations and institutions. This is again, Ajit has pointed out that we need to integrate or interact with international bodies, particularly IAU offices. And you heard that there are IAU centers also in education is coming up within the country. We need to also talk about more synergy with the Planetary Science Museum and other centers. So there is a special session I will again encourage you to attend with the planetary directors and ASI and amateur astronomy bodies. So I think yesterday also it was pointed out that many initiatives at different times was sort of kicked in, but continuity was a problem. So now we are looking at addressing the issues which have been already identified, and then how to integrate that. Other Indian science societies, international astronomy societies, these are major bodies where we were to we initiated this participation of certain international unions or societies, their president to be invited. In fact, in Kashmir we did that many years back. Of course, this year we could not do it. So I think we will initiate that as well. And they were so much impressed. The Korean and the Japanese were here, and they were amazed to see the growing astronomy community. So I think we will have special sessions on that. So what is important is the community feedback. So I, again, emphasizing on this fact, we have just started our journey in this Golden Year celebration, and we would come back to you through our feedback, different medias and so on. So please give us your suggestions, and we'll try to incorporate that to take things forward. So that's my opening remarks. I will now invite Professor Prabhu. I hope he is online. Yeah. Okay. Yeah, Professor Prabhu, would you like to share your screen, and we can have the first presentation?
Yeah, can you hear me?
Yes, very well. Yeah, we can see your screen also. You can get into the full screen mode, please.
Yeah. Okay.
Please. Yeah.
Okay, thank you, Dipankar. So I'm speaking on the ground-based facilities for astronomy in India, particularly optical and the very high energy gamma rays. And the first large telescope I had seen was in the year that ASI was formed in 1972. I was a student of MSc. That I have shown here in the left bottom corner. There are two telescopes. One on the left is a 6-inch telescope, and one on the right is 8-inch. And I looked through the 8-inch telescope to several objects in the sky. And since then, we have moved forward quite a bit. And the latest is the 3.6 meter reversal optical telescope. So I have shown here a whole lot of telescopes we have got in the interim period, and hoping to get a 10-meter class national large optical telescope in future. And in addition, on top, parallel to the diagonal, we see the development of solar astronomy, a 38 centimeter telescope, then a 50 centimeter telescope, and hope for a 2-meter telescope. And at the bottom, we have got the very high energy gamma ray telescopes, Pachmari, the Mount Abu, and in Hanley. So, in the ground-based astronomy is possible only in two particular areas. One is the radio region where everything comes unobstructed from the wavelength of about a few centimeters to wavelength of a few decameters. So the radio waves come in without any obstruction. As you go to lower wavelengths at or higher frequencies, the atmospheric molecules start absorbing by various amounts. And then we come to this infrared and the visible region. And actually, visible region is also not as transparent as the radio. And as you go to higher and higher elevations, the absorption gets reduced because you are leaving many molecules behind and climbing up. It will be advantageous to go to higher altitudes. And the entire region, we sometimes call it optical or optical infrared. And that is because the technology used for detection, the telescopes are extremely similar, detectors are similar. So only difference would be that when you go to something like 10 micron, 10 micron is where all the emission of 300 degree Kelvin or ambient, that is 27 degree Kelvin peaks. So there is enormous amount of radiation coming from everything around you, including the telescope and so on. So you need to improve in that aspect. Otherwise, up to about 3 microns, things are easy. 5 microns, some amount of contribution from ambient starts becoming important. Cold deserts like Hanle are very, very good for that purpose. And so I define optical by this, but we have gone only up to about 5 micron, optical and near, the visible and near infrared. And high altitude also helps you go a little bit into the deeper in the ultraviolet, going to about 3,500 angstroms. And I also did very high energy gamma rays because these gamma rays are when detected using Cherenkov technique. That is the gamma ray impinging on the atmosphere interacts with the nuclei in the molecules and gives rise to electron-positron pairs and a cascade of particles which move at relativistic speeds and emit Cherenkov radiation cone in the forward direction. And that light is mostly blue and UV, which can be measured using the optical techniques. So I've added this, but we have had a more detailed talk by Varsha Chitnis on Saturday in the instrumentation and techniques session. Those who have attended would have heard about it already. And also in the workshop 4, Amit Shukla described this before going on to the science. And the history of telescopes in India is quite old. I have not put everything. I was hoping that Rajesh Kochar would have been here to talk about it. It is unfortunate that we have lost him. And there are people probably in the audience like Ramesh Kapoor who have tried to see how early telescopes were used in India. But I am trying to list here the telescopes which were at the observatories. So it is basically history of optical observatories in India. So one of the Madras observatories set up in 1792 using a 3-inch telescope brought in by a civil servant, William Petrie. And Pogson was its director for more than 3 decades. But after him, it was decided to move the observatory to Kodaikanal and concentrate on solar astronomy because the British got interested in seeing the how sun affects the monsoons. And at that time, the regular astronomy it flourished in other places. The Naigamwala in Pune got a 16.5-inch reflector using the funds donated by Maharaja Tak Singh Ji of Bhavnagar in present-day Gujarat. And he upgraded to 20-inch telescope later. It is called Bhavnagar telescope. Upgraded probably means that the older telescope was bought back. And a 15-inch reflector was procured by Nawab Jafar Jung, a nobleman in Nizam's court in Hyderabad. and at Begumpet, the Nizamiya Observatory was established. And its 8-inch astrograph was used in the Car2CL project coordinated all over the world to take the photographic, make a photographic atlas of the entire sky. And the modern period begins with the planning by Meghnad Saha in 1945. The committee which was planning the future of development of A&A in India recommended the establishment of an astronomical observatory, the telescope of large aperture. What aperture was not specified. The largest was 100-inch at that time at Mount Wilson, and 200-inch at Mount Palomar was under construction. And the 100-inch is 2.5 meter, for those who have forgotten inches, 200 is about 5 meters. And the modernization of Kodaikanal Solar Observatory and establishing a Schmidt telescope somewhere and astronomy at telescopes, astronomy and telescope at universities, etc. It's quite detailed report. And now, why an astronomical observatory apart from modernization of Kodaikanal Solar Observatory? Because it was already noticed that Kodaikanal Observatory was not an excellent site except for a few hours in the morning when the weather was very calm. And once the ground heating began, it was not very useful for sun also. And night time was quite often the seeing used to be very poor and affected by both monsoons and so on. And so one of the major requirement of optical observatories is site. That the site should have number of clear skies, low atmospheric turbulence, low aerosols, and so on. And higher altitude helps in going deeper into the ultraviolet and in the infrared. But apart from that, we need to be away from civilization. The sky is our first constraint, and after that is the human civilizations. Human beings can be your best friends as well as worst enemies, and civilization is highly polluting. So we need to be away from it, and particularly light pollution is what we talk about, but air pollution also affects us. And then onwards, we have found sites in Nainital, near Nainital, Manora, Devastal, at Kavalur, at Mount Abu, Giravali, Hanle, and so on. And for solar astronomy also, we have lakeside sites, which helps the large amount of water body, helps in absorbing the solar heat and stabilizes the atmosphere around, turbulence is reduced. So how we went about searching this is that Kodaikanal itself is a good example that from the port of Chennai, Madras, to the peak of Kodaikanal, the observatory was shifted for better observing conditions. And early on itself, it was realized that there could be better sites around the country. In 1913, John Evershed went on holidays to Kashmir and was impressed by the site conditions there. And 1915 to 16, he officially conducted a site survey a continuous site survey in Kashmir Valley. And 1955, Manora Peak was identified by Venu Bapu, who was appointed chief astronomer of the UP State Observatory in Benares. And as soon as he reached there, he convinced the authorities and the Chief Minister Sampurnanand that it is better to move to a higher altitude mountain site than the dusty plains of Benares. And this was identified immediately. And he came over to Kavalur as the director after A.K. Das had retired. I had shown this picture earlier, where Meghnad Saha on the left and Venu Bapu on the right. And A.K. Das was the director of the Kodaikanal Observatory at the time of the Meghnad Saha committee, and took all this recommendation seriously. And Arvind Bhatnagar was with Bapu at UP State Observatory and moved with him to Kodaikanal, then went abroad for a PhD and came back to set up a solar observatory in the country. And so here I am identified in 70s the best site in the country based on the meteorological records available already. And in 1974, the first meeting of the Astronomical Society of India in Hyderabad, there was also a workshop. The first workshop associated with the Astronomical Society of India meeting, which was on infrared astronomy, and submillimeter probably was included, but I remember infrared astronomy clearly. And if for infrared astronomy, you needed a very dry site, because water vapor absorbs a lot of infrared radiation. And Bapu also undertook some amount of additional site survey south of Pachmadi in Madhya Pradesh, because he wanted to be closer to the equator to get as much of skies as possible. As you go to the north, you start missing the southern skies, but sky conditions improve. So he concluded that while the sky conditions improve as you go towards north, number of clear skies improves, but the amount of sky lost is also significant. So there is no strong advantage up to the central India. So there was need to go to an exceptional site if you are satisfied with only northern and a little bit of southern skies. The sky conditions should be exceptional. So he proposed site survey in Leh and laid some groundwork in 1981-82. Unfortunately, he passed away in 82. But before that, he had sent a letter to Arvind Bhatnagar urging him to proceed with it. And Arvind Bhatnagar was already identified for this as the national coordinator for the site survey. So 1984 to 89, it was DST supported site survey, which was undertaken in Leh. And then it was apparent that we have to move to southeast of Leh for better conditions. And we moved to that area in 1992 to 96 with Ramnath Kaushik and Ashok Pati, looked at all the weather data available, topographic information. And we had a recce of 6 sites, and finally Hanle was identified during this period. And while I'm on this, I would like to highlight the contribution of the Taksing-Ji Observatory. So apart from the 20-inch telescope, it had other telescopes too. The 20-inch telescope was transported to Leh during this 1984 to 89 period, and it did quite a bit of observations of the sky there, probably more than anywhere else. And there are smaller telescopes which are used, a telescope as well as a prism spectrograph, which was used for solar observations earlier. And Evershed had taken it to Kashmir Valley in 1915 to 16 for the site survey for solar astronomy in Kashmir Valley. And the sites are distributed like this. I'm showing this on the weather pollution, light pollution map of India. I've seen from the sky, the amount of light which is sent out to sky from various places is shown. Red is the brightest, and blue is faint, and still fainter is gray after that, gray level, and the darkest gray portions are very dark. And we have the Kodaikanal, Kaulur, Chennai, which is Madras Observatory, and Giravali, Udaipur and Mount Abu in Rajasthan, and Varanasi, where Bapu didn't want the observatory, and then the Nainital region, which can be seen, you can distinguish between Manora Peak and Devastal in an expanded version on the right side. And we have the Hanle and Merak sites, which are in expanded, you'll see here. And the nearest light sources are Leh in India, and also this is a place called Sichuan in Tibet. China had developed a new township there. It is very close to old village of Ali, where Chinese are developing the astronomical observatory. And optical facilities next require an aperture, and aperture's size is continuously bigger and bigger. Telescopes are being built in the world, and you may say, why not go for the biggest telescope? But to reach to the biggest telescope, you need the smaller telescopes, both as technology development, but also for science. We cannot do all the science with the biggest telescopes, which are reserved for the foremost science on the faintest objects, highest resolution, and so on. To mature your science up to that, you need smaller telescopes. And mostly in the world now, 1 meter size telescopes are used for dedicated programs. 2 meters are available for groups, and 4 to 10 meter are institutional or national telescopes, and 30 to 40 meters are multi-country collaborations. And in India, we have 1 to 2 meter telescopes at institutional level, and 2 and 3.6 meter at national level. And planning a national 10-meter telescope is going on, along with participating in 30-meter telescope. And this 30-meter telescope participation would jumpstart our involvement with large telescope, as well as technology transfer for the building of 10-meter telescope. And the solar astronomy, we had 15 centimeter to 50 centimeter telescopes we have now, and we are planning a 2-meter national telescope. This can be compared with the 4-meter class telescopes which are there in other countries, and the Chinese, which is planning a telescope, is something like 5-meter in equivalent aperture, but 8-meter in resolution. And you see that there is a kind of factor of 5 to 6 in the largest telescopes in solar to largest telescope in the optical region. And this is both because of technology required for bigger and bigger telescopes in sun, where so much of heat is also concentrated, as you pointed to the sun, and also because there is so much of light is available, we don't really need to go to the biggest telescopes. So if you consider that, so 0.5 meter telescope for solar and 3.6 meter telescope, optical telescope DOT we have are comparable, and we are now equally behind the world in both these. Though in the past we are far ahead in solar. When in 1920s, Kodaikanal was counted among 3 major observatories in the world, other 2 being Mount Wilson and Madon. This used to be in the textbooks of those periods. And larger telescopes need active and adaptive optics, so this is additional technology one has to develop. And all telescopes require focal plane instruments, which will keep on improving with technology. We have imagers, spectrographs, various resolution spectropolarimeters, and the interfaces which can improve the multiplexing of observations. And I'll quickly go through the observatories we have and facilities we have. Kodaikanal Solar Observatory has currently 38 centimeter telescope, and this was developed as a part of modernization suggested by Meghnad committee. And this one has is installed in a tower and tunnel telescope building, where a 11-meter high tower is installed. The light is collected from 11 meter above to avoid the ground turbulence, and then it is taken underground into a tunnel where the temperature is stabilized. There is a 60-meter long tunnel in which this telescope is installed, giving a 5.5 angstrom per millimeter image, and we have instruments there, particularly a spectrograph and so on. We have the legacy instruments of spectroheliograph, which are built very early, and the 15 centimeter telescope, which came from Madras and was converted to a photoheliograph. And all this more than 100 years of data is available in the next slides. But in between, we are now modernizing the solar imaging from the instead of spectroheliographs, which are based on photographic plate. We can do the filtergrams now with CCDs, and so broadband, calcium 2 narrowband, and H alpha narrowband. These images are being taken with independent telescopes now.
Prabhuji, you have 5 minutes.
Yeah.
You have 5 minutes.
Yeah, thank you. Yeah, I'll speed up. Then the 50 centimeter Udaipur Solar Observatory is currently the biggest 50 centimeter telescope is there with various instruments, and older the Gong heliosismology station is also there, and the future is a 2-meter telescope. And the suggested site is at Merak in Pangong Tso, where there is an incursion in the Pangong Lake, where already some site survey was conducted, and a 15 centimeter H alpha telescope is installed there. With 15 or it is exactly, sorry, it should be, I think it is 20 centimeter. It is exactly identical to the one which you have got in Kodaikanal. Okay. And the birth of modern optical astronomy started with 1 meter class telescopes at Japalrangapur in 1968 and at Manora and Kavallur in 1972. Manora, the UP State Observatory then changed into Aries later. The emphasis was on photometry early days, and spectroscopy is added to some extent later. And Kavallur was the emphasis on spectroscopy. And one has moved from photography plate to photomultipliers and charge coupled device and so on over the decades. And various instruments, different generation instruments have been built. And 1M class telescopes are still, they continue to be relevant for various specific programs, like the 1.2 meter Guru Shikhar infrared telescope was installed in 1994 with emphasis on infrared astronomy. But PRL has a very active tradition of building instruments. So they have optical and infrared instruments being built continuously over this period with PARAS, the precision radial velocity spectrograph currently operating there. And 2010 and 2014, the 1.3 meter telescopes came up at Devasthal and Kavallur. Both are wide field imaging telescopes. And 2018, a 70 centimeter Growth India telescope was set up in Hanle. It's fully automated robotic telescope to observe transients, any near Earth objects, and so on. And 2 meter size telescope began with Venubapu telescope in 1985. It was built mostly indigenously, and this was what was considered as the dream of Saha, but came some 40 years later. And it has currently a prime focus imager, but prime focus I think is not generally or not often used, Cassegrain spectrograph, and fiber-fed high-resolution spectrograph. And the next 2 meter telescope was at Himalayan Chandra telescope. It is remotely operated national facility, and its instruments are a faint object spectrograph camera for optical and similar instrument in the infrared developed by Tata Institute of Fundamental Research in Infrared Astronomy Group, and a Hanle HL spectrometer for high-resolution spectroscopy. It was developed as a first step towards the National Large Optical Telescope. The proposal name at that time was HIROT, Himalayan Infrared Telescope, and the committee which evaluated the proposal recommended that we should start with a small telescope, 2 meter class telescope, and get remote operation capability and develop infrastructure for the observatory. That has been done. This is a telescope there. And continuing on the 2 meter class, IUCA obtained a 2 meter telescope where it wanted it for observatories, teaching, training, and various things. So it needed to be close to them. And then currently 2.5 meter telescope is has just been installed at Mount Abu by PRL. And 4 meter class, we entered with the Devasthal optical telescope in 2019. And it also has a faint object spectrograph camera. And the TIFR has developed an infrared camera and infrared imaging spectrograph, image-cum spectrograph, 10 spec. And a high-resolution spectrograph is under construction for this. This telescope has active optics to keep it in good, keep the mirror in good shape, and adaptive optics is possible with this. And now I'll just show you the size of telescopes bigger than about 4 meter in the world against various times, and the development in India, 1 meter class, 2 meter class, and then the 4 meter. We have finally reached the 4 meter class, and in this period, others have gone to 6 meter, 8 meter, and 10 meter, and so on. So it is indeed time that we also enter this stage. So the 30 meter is what we have immediately decided to join and started working on. And so the experience with 30 meter telescope will be useful for National Large Optical Telescope about 10 meters. And I understand the proposal is already taking good shape. And the site for this could be anywhere in around Hanle. There is plenty of space. Okay, I'll just briefly tell about high energy gamma ray astronomy. Much more detail was there in Varsha, and probably if recorded talk would be available later. As I told you earlier, that the gamma ray photons can be observed through Cherenkov radiation, which is secondary radiation coming in. But one has to reject the cosmic ray induced events, because cosmic rays are also particles entering the atmosphere, and they also give rise to a shower and Cherenkov radiation. And two techniques are used. The TIFR technique started with a wavefront sensing technique, which will try to reconstruct wavefront sampling. It samples the wavefront at different positions in this in the Cherenkov cone, and constructs the wavefront of the Cherenkov light coming from gamma ray. So effectively leaving out the cosmic rays. So they started in Ooty, then moved to Pachmari, and then came to Hanle with IIA collaborating to build the telescopes also. This is high altitude gamma ray array. And the BRC started at Gulmarg with imaging Cherenkov telescopes. So this images with many telescopes and an array of camera in the focal plane. The event itself, the event will be circular if you are pointing it exactly towards it. It will become elliptical if it is coming at an angle. And whereas the cosmic rays will give an irregular shape one. I just saw it on Saturday in a presentation by Kurana and the technique talks. Okay, so I have left out talking about the projects we have been working with elsewhere outside India, and just show it in this particular slide. The 30-meter telescope project, most likely at Mauna Kea. So it is giving us experience to build our own optical telescope. And Cherenkov telescope array, with in international project, we are yet to fully participate, but BRC is involved and TIFR involved with it, and Science Institute also getting into it. And sometime when we formally join it, utilizing the in-house experience we have in very high energy gamma ray astronomy. So this is my last slide. I have not put a thank you or best wishes slide this time. Thank you for listening to me.
Thank you very much, Prabhuji. We have time for one or two quick questions from the audience. First, I'd also meanwhile request the online participants to put your questions in the chat box. Are there any questions from the audience here? Please raise your hand. You can also use the raise hand option in the online. Yeah, thank you very much, Prabhuji, for giving this overview. I just wanted to also mention that in the forthcoming IAU General Assembly, this was also part of our IA 50 celebration, that we are going to put a stall there. And I would request anybody attending the IAU General Assembly to please come forward and man this stall. I will be planning also to go, because we are not sending a separate team. We'll be trying to take in rounds and do it. These are opportunities for the international platform to highlight our observing facilities and so on. Yeah. So Priya has asked a question. Could you let us know of progress of the NLOT?
Yeah, the best person is probably Anupama. She talked a bit on that in the presidential address as part of the Megavision document. And I think a concept report has been given to the government. And there has been an IIA, I remember that a lot of prototype activity was done while working on the various actually using the experience at the TMT lab. So say similar items.
Yeah, Anupama is here. She is ready to respond further. Please, Anupama.
Yeah. What you said is right, Prabhu, and the work is still going on, although at a kind of a slow burn. We have progressed in making some initial design for the primary mirror and working out the optics and the errors and other things. And there is also some amount of work going on the structure of the telescope, but this is going on a slow burn. So far, we have not yet heard from DST for the initial proposal that has been submitted. We are waiting to hear from them. That's the status right now.
Are there any other questions? We are just setting up the next talk. Meanwhile, if there are any other questions on the online or offline, we can take it. If not, then let us thank again Professor Prabhu for a very nice overview of the historical perspective of facilities. Now I request and invite Dr. Seetha for giving us the perspective from space platforms, Indian space platforms. Let's share the screen. Yeah, fine, please.
Yeah, good morning to all. It's a great pleasure for me to give this talk on tracing the history of space astronomy within the country. And I have been part of most of this journey, though not in the initial stages. And I hope it will grow much more in the coming years. So let me start with the beginning. The study of cosmic rays. There was a lot of study of cosmic rays in the country at PRL, etc. And the two most illustrious among them, as you know, Professor Homi Bhabha and Dr. Vikram Sarabhai, did cosmic ray research using balloons from IAC, and I think that has become famous even in the commercial platforms. Meanwhile, in 1957, the first satellite was launched by the USSR called the Sputnik. And immediately almost, the International Council of Scientific Unions, which was called ICSU, now it is called the International Science Council, ISC, they established what is called the COSPAR. It is called the Committee of Space Research, because they anticipated that this is going to grow into a big area of research. So this was done in 1958, called COSPAR. COSPAR is now sort of parallelly run just like the IAU, if you want to draw parallels, but it's not at all parallel anyway, because it also consists of many, many countries, many space agencies, which are members of COSPAR. The first COSPAR symposium was held in 1960. The Indian National Committee for Space Research, which is called INCOSPAR, was established quickly in 1962 under the Department of Atomic Energy. Yeah, so, and the Indian Space Research Organization was formed in 1969, again under the Department of Atomic Energy. Incidentally, I might say here that the Indian National Science Academy, INSA at Delhi, actually is the interface between India and, for example, the International Science Council, and it also sort of coordinates the national meetings of IAU, Indian COSPAR, INCOSPAR, and URSI. So that is the place to go if you want to have details of the meetings, the national level meetings which are held on this. So I talked about balloons. So where is the need for space astronomy and where is the need to go to balloons? Already Dr. Prabhu mentioned that only the radio wavelength is available right up to the surface of the ground. And of course, optical is visible with a little aberrations, etc. And the higher you go, it's better for optical and infrared. So the balloons are used to go up to heights of 30 to 40 kilometers to access both the infrared windows over here and the gamma ray, high energy X-rays and the gamma ray windows over here. But primarily the ultraviolet and the X-ray bands are blocked by the Earth's atmosphere as is shown in the pink regions. And therefore, in order to access both UV and X-rays, we need to go to at least rocket heights, which is of the order of 120 to 150 kilometers and above. And therefore, rockets and satellites are the best modes to study UV and X-ray astronomy. Though, as I said, high energy X-rays can be studied using balloons, and it has been done. Continuing the legacy of balloons and then going on to rockets, the initial experiments in astronomy were also done using balloons and rockets. The balloon facility is now established at Hyderabad, and it is called the TAFR balloon facility. It is at present headed by Professor Ojha here, who is the associate chair. And they can fly balloons right up to 50 kilometers. And of course, the mass of the experiment which they can carry varies depending on the heights which have to be reached. So they conduct a lot of experiments, not only in stratospheric, to study the stratosphere, etc., and also for infrared and gamma ray astronomy. In parallel, as I said, when the INCOSPAR, etc., started, the rocket facility was started in Trivandrum by Dr. Vikram Sarabhai. And in 1963, the Tumba Equatorial Rocket Launch Facility was established. Initially, it was the foreign rockets like the Centaur and the Nike Apache, which were brought and flown from here. And the rocket launch, not only the rocket launching, but also the data reception, the telemetry, telecommand facilities were established at TERS here. And that gave the impetus for us to start the space program within India. So this is an artistic rendition of the rocket facility at Tumba. So just like the balloon facility continued, and it is still continuing with better capabilities, the rocket launches are also continuing both at Tumba and also from Sriharikota. So we can fly up to rockets up to 200 kilometers, etc., from Tumba, and for higher heights, all the way up to 500 kilometers from Sriharikota. Again, the mass of the experiment varies depending on the heights which you want to go to. Then coming to the next step, of course, so that was the first phase of space astronomy using the balloons and the rockets. Then came let me also state that the balloon payloads are recoverable and they have lifetimes of few hours of observation, whereas rocket payloads have only few tens of minutes of observation and they are not recoverable. So then it was decided that for longer observation times and as per the vision of Dr. Vikram Sarabhai, that we should use the space for societal benefits. And therefore, remote sensing and communication were the prime areas which was decided to be the thrust for the space program. And so in 1972, the Department of Space was established along with the Space Commission, and the ISRO was also brought under Department of Space. And in parallel, in 1972, the scientific satellite project was started to build Indian satellites. And this was brought from Trivandrum to Bangalore, thinking by Professor U.R. Rao, who headed this project in the beginning, to sort of initiate that Bangalore already had the facilities of the Bharat Electronics, the Hindustan Aeronautic Limited, etc., which they thought would definitely aid this satellite building program in terms of industry support. So that is how it started in Bangalore, and the Department of Space office also started in Bangalore. So the first satellite experiments, as you all know, so those I went slow because many of you may not know. The first satellite experiments were started with Aryabhat and Bhaskara 1. The Aryabhat, as I said, was initiated in 1972 with just 40 people, 20 from PRL, 20 from Trivandrum, who came here. And then they recruited about 100 to 150 people, both engineers and scientists. And with just 200 people, literally starting from the scratch, the Aryabhat was built within 3 years, which was given to them. And this was launched in 1975 using the USSR launch facility and the launch vehicle. There were 3 experiments, one in astronomy, one in aeronomy, and one in solar physics. And these experiments were developed primarily by TIFR and PRL, which also was involved in the initial development of both the balloon and the rocket experiments. So the Aryabhat and the Bhaskara 1 also carried an X-ray experiment. The experience which we gained using this was the development, testing, and space qualification of the science payloads. And also the procedures of how this should be qualified, etc., in future. Along immediately after this, we also flew an Indian cosmic ray experiment called the Anuradha on board NASA Space Lab 3. This was a passive experiment. It was taken on Space Lab, brought back, and thin layers which recorded the cosmic ray events were analyzed at TIFR. So you have the references here for seeing the history of these experiments and also the results. Then started while these were satellites which were launched using the foreign satellite launch vehicles, and of course we also had after this the remote sensing program and the communication program, which was started with the Apple satellite, going on track. But we decided that the science experiments would have to wait for the Indian satellites flown on Indian launch vehicles. And therefore, we waited for the Rohini series of satellites, which were flown on the augmented satellite launch vehicles. The first Rohini satellite itself was launched on using the SLV, called the satellite launch vehicle. And then we needed much more capabilities for payloads. And so the augmented satellite launch vehicle, which could launch 100 kgs capability of satellite, and on which we launched the gamma ray burst experiment and the retarded potential analyzer by the NPL. We were given the payload mass of just 5 kg and a 1 watt power capability. And at that time, the detection of GRBs was done in 1960s, which was announced in 1973 using the Vela satellites, and they were very relevant scientific topic. And so we decided to fly this gamma ray burst experiment from ISRO, and it is a relevant topic even now. At that time, gamma ray, the localization of gamma ray burst was supposed to be established using the multiple satellites and with triangulation in the sky, the same principle which is now being used by GPS satellite for triangulation on ground to find the position. Yeah, so the first two launches of ASLV unfortunately failed, and we were also in parallel. I should mention here the group in ISRO in parallel were using this time to build photometer to study optical counterparts of X-ray emitting objects in using the telescopes at Chengalur and later Nainital and also Mount Abu. And we cherish the experience we gained using the optical observatories. The experiments which were successful with the gamma ray burst experiment was the SROS-C and the SROS-C2. The SROS-C, of course, went into a lower orbit than planned, but the SROS-C2, of course, was a great success, and we detected over 50 gamma ray bursts, and we also contributed to the interplanetary network for localization by triangulation. Of course, by then, the Compton Gamma Ray Observatory was in orbit, and they could detect many more gamma ray bursts, almost one per day, and that took over the research in gamma ray bursts.
So you covered 16 minutes.
Okay. Yeah. So timing of these experiments is this I said because timing is very important because otherwise it gets outdated. Yeah. So we also flew piggyback experiments on other satellites. The Indian X-ray astronomy experiment by TFR, as I mentioned in my earlier talk also, was flown on IRSP-3, a remote sensing satellite. So we only got 3 months during the monsoon months to observe the sky when the remote sensing payload could not observe the Earth. And using those 3 months, we actually observed several X-ray binaries and established that we could point to individual stars in the sky using space platforms, and that led to the proposal on AstroSat. I want to mention also here that the XAE was proposed in 1982, well before the launches of the gamma ray burst experiment, but because it was an experiment of the 550 kg bracket, it needed a satellite much heavier than 100 kg and therefore had to wait for the Polar Satellite Launch Vehicle to launch it. So the proposal for AstroSat came in 1996, and of course the project proposal also was submitted in 2004. I'm mentioning this here. Keep it in your mind because I'm going to mention some things which came ahead of it. Yeah, then the solar X-ray experiment was launched on GSAT-2. So you can see we used the IRS platform, we used the GSAT platform, and any platform which was available. In parallel, there was also the RT-2 experiment, which was again flown on an USSR satellite. Then comes the third phase, which is the phase of space science missions. The Chandrayaan-1 and the Mars Orbiter mission, of course, came ahead of the AstroSat because there was a lot of indigenous development activity which had to be done for the payloads and the satellite of AstroSat, which took a long time. And Chandrayaan-1, Mars Orbiter, and Chandrayaan-2 are what we call primarily ISRO-defined missions, where there is a large component of technological developments which have to happen, and therefore the timeline, the schedule, etc., is primarily defined by ISRO. And this also could be made because of the operational availability of course, the versatile PSLV and the GSLV Mark II, and of course for Chandrayaan-2, the GSLV Mark III. Chandrayaan-1 mission was launched in 2008. It had high resolution cameras. It was an Indian mission with significant international participation. 5 Indian payloads, 6 international payloads, of which 2 payloads were in close collaboration with Indian teams. Of course, you know about the detection of water, OH molecules in minerals, and detection or confirmation of detection of water, which is attributed to Chandrayaan-1. But there were also several other results like that much of the solar wind protons is indeed reflected back from the lunar regolith, and it is not totally absorbed, which was the theory for actually finding water molecules on the Earth. So at least 20%, if not more, is getting reflected away from the lunar surface. We also had then the best 3D images from Chandrayaan-1. We also detected the water vapor in the thin exosphere of lunar, the moon, using the moon impact probe. And several other things, the detection of sodium using the KICS experiment, etc. Then going on to we have over 200 publications using Chandrayaan-1, and the data is made open using the Indian Space Science Data Center, and 600 users are using that data. Mars Orbiter mission, again, ISRO-defined mission, technologically great for reaching outside the Earth-Moon system and going into heliocentric orbit and reaching the Mars orbit. We have a limited number of publications, about 20 publications. And so we have the study of, again, the exosphere of Mars. We also have the mapping of the Mars in 1.65 micron using the payload, which was flown for detecting methane. And we also have several images for which the Mars Orbiter mission is famous for. And this is a shield volcano, which looks very much like an upturned penguin, if you like. And many such images are there, which we have released, that the artistic community may also make of this. It is still in orbit, and we hope that it will continue in orbit. Of course, the AstroSat, I've already talked about the details of AstroSat, and further details can be had from the Journal of Astrophysics and Astronomy special issue, all the papers of which are downloadable. And again, 200 publications already from AstroSat, and we are going strong on it. We have 1,400 users, and this is the first observatory where we are making observations like a space observatory with pointing to proposal-based stars or stellar systems in the sky. Then the Chandrayaan-2 orbiter, a detailed study of topography, improved payloads compared to what we had in Chandrayaan-1, and many of them indigenous now, extending the infrared spectrum beyond 3 micron, because I didn't show you that we couldn't cover the water line completely, and so we wanted to go all the way to 5 microns so that we completely cover the absorption line of the water. And we also established the thermal background so that the absorption line could be properly detected. And of course, the higher area for the X-ray detection of X-ray fluorescence, higher resolution solar spectrum payload. And now we are doing the synthetic aperture radar with 2 bands, the first time on a lunar orbit, both the L and S band. And of course, the high resolution imager with which we are getting, again, much better images, better than 0.3 meter resolution. So these are the list of publications which are already coming in space and coming in the journals. And we also have, taking the astronomy context, we already have high resolution spectra of the sun even in the quiet sun period. Yeah, so launched in on 22nd July. Unfortunately, of course, the lander and the rover didn't work, but the orbiter has some great things. Science experiments lead to a lot of new developments because they are more demanding. And so we have had facilities established. I told you about the Indian Space Science Data Center. There is also the MGK Menon Clean Lab for UV integration at Indian Institute of Astrophysics. It has a 100-class facility, and now they are even planning a 10-class facility, 10 class, 100 class, etc. indicate the cleanliness level. Usually satellites are assembled in 1 lakh class. So you can imagine the level of cleanliness we need for UV assembling and testing the UV experiments. Capacity building, as I said, hundreds of registered users. Miniaturization, because Mars orbiter missions, etc., had just 15 kg allotted for payloads. So it led to a lot of miniaturization. Spin-offs, thermal coatings, pressure transducers, adhesives, lightweight composites, hold down mechanisms for doors, release, low energy X-ray spectrometer, and now there is a lot of technology transfer which is happening. Industry interface has also happened at the institutes which built the payloads. Gold coating for X-ray mirrors, for example, was done with for the SXT mirrors of AstroSat, was done with industry interface. Precision machining was done, and now, of course, you have the New Space India Limited, which has been established within Department of Space, which will now carry forward this industry interface, and we hope it'll grow in large amount. Of course, all these missions have enthused a large number of students and public towards space. 1 minute, 2 minutes?
1 minute.
Okay, 1 minute. Okay, the upcoming missions, XPOSAT, which has 2 payloads, POLIX and EXPECT. You heard about EXPECT in yesterday's session. POLIX is a payload to study the X-ray polarization, and we are looking forward to this mission. Aditya L1, it has now 7 payloads, 4 experiments to study the sun, 3 experiments to do in situ observations in the L1 orbit around the Sun Earth L1. And we already have 20 publications from Aditya L1. Yeah, future missions, Gaganyaan, the human space mission. Biology, this will be experiments which will be carried and brought back. So now experiments connected with biology are being considered, and they are being developed, and the final experiments which will be carried will be decided slightly later. And of course, other missions to study the ionosphere and planets. Thank you.
Thank you very much.
Time for very quick comments or questions. Anybody in person here? Online participants, you can raise your hand. Yeah, the first question comes from Anupama on offline.
You mentioned about the gold coating. Which company did that?
KP Singh is the best person to answer that. He identified a company, trained them.
Yeah. So this was actually some young entrepreneur who came from US, having worked with Alcatel. He approached me that he can help me with gold coating, making the sputtering system. The Pune-based company, Advanced Optics company, and he made the very first gold sputtering system with a large gate wall and so on to put the glass and rotate and automate it. He did it all himself and got things built in Pune. That was Advanced Technology, we called it, his company. And after that, he has now become famous, and he built for BRC, IITs and so on, wherever they wanted a sputtering system, he built. So this was a almost led to the beginning of this entire. So it was very happy.
Yeah, incidentally, there is also gold coating being done for the collimators of the class experiment and the expect experiment. In case you.
Dipendu?
Yeah, first of all, congratulations to ISRO for opening up to the astronomy community and looking up at astronomy missions. Now, having said that, we are still far behind some of the more developed nations in both the scope as well as in the number of missions that we are sending up. And to get there, we also need to be able to create the human resource for enabling more participation from outside of ISRO centers.
Mm-hmm.
There are certain missions which we just come to know from newspapers after instruments have been selected.
Mm-hmm.
I know that ISRO is trying to change that, trying to create workshops for involving the community, but all after things are launched. Is there a sort of a new thinking at ISRO that for certain classes of missions which are driven by primarily through inside ISRO, there'll be more attempts to incorporate universities, institutions, right from the proposal stage, the instrumentation planning stage, so that students can be involved with these missions right from the beginning. So you get more bang for the buck and more papers and science out of these instruments.
Okay. Yes, as I said, the Chandrayaan-1 and Mars Orbiter mission were totally ISRO missions. But of course, for Chandrayaan-1, for the international payloads, there was an announcement of opportunity. But post Chandrayaan-2, we have invited proposals. For example, for the Venus mission, there was an announcement of opportunity. In fact, there have been universities and other teams which have proposed for experiments, and they were even funded for some developmental activities and so on. So both for that and the Mars Orbiter mission 2, we had opened up. Those were all done using announcements. And of course, for the astronomy missions, we do make announcements. Aditya L1 also was made open because after Aditya got converted to L1, we again made it open. Yes, the Space Science Office has, when I was there, has recommended that all these science missions should be open announcement of opportunities. Of course, depending on the capabilities of the teams, you might decide whether they should build it alone or join hands with somebody so that they gain experience to realize the final result. But I don't think it's going back to the old thing, I hope. I think it will be made. Even the ionosphere mission was made open.
Thank you very much, Seetha, for your voyage through the heliosphere on the Indian space platform. So, just need to stop sharing. So next, let me invite Jairam Chengalur, who is online. We'll just stop sharing here. Yeah, Jairam, you can go ahead and try to share your screen. So now this will be.
Good morning. I hope you can see that.
Yes, we can see, and the screen is also in full screen mode. Yeah. Thank you very much. Please go ahead, Jairam.
Yeah. Okay. Thank you, Dipankar. So I've been asked to talk about the past, present, and future radio astronomy facilities in India. And, given the occasion, the 50th anniversary of the Astronomical Society of India, I thought it would be good to focus a little bit more on the past. So that's what I will be doing on the talk. And partly this is also because I think there are, some interesting stories from the very early days of radio astronomy in India that we don't hear that often about. And I felt this is a good occasion to talk about them. The entire talk won't be about the past, of course. I will say some things about the present, as well as developments planned in the near future as far as radio astronomy facilities are concerned. There's one more caveat I should give before I start. The title is Radio Astronomy Facilities in India, but I'm going to interpret that somewhat liberally. I will also discuss some facilities which are not located in India, but in which Indian radio astronomers have played a significant role. The last thing I'd like to just acknowledge before I start is, the help I have received from a large number of people, and I hope I haven't missed anybody over here. So I'd like to acknowledge the inputs from all of these people and the data and inputs that they've sent me over the last few weeks, without which it would have been very difficult for me to make this talk. But of course, any errors of omission or commission are mine. So with that, let me start. So early radio astronomy in India started actually at Chengalur Observatory. And it's very interesting to note that the first observations date to the early 1950s. And that's not really very long after the first solar radio observations were reported by Grotriba in 1944. And less than a decade later, even though this is a very new and nascent field, there's also already work being published from Chengalur in India. This work was led by A.K. Das, the director at that time, about whom we've already heard about in the first talk from Prabhu. And I understand that a lot of the science was led by him, but there was also B.N. Bhargav over there who was building the instrumentation. This is my understanding. I could be wrong, and I request people who know better to correct me, but I understand that a lot of the instrumentation was built by B.N. Bhargav, who was also interested in geomagnetic phenomena. So one of the early observations were of a radio burst, which got correlated with an associated geomagnetic disturbance. So they're seeing the effect of what one would call solar weather now on the Earth. And there were also correlations done with a solar eruption and associated radio emission. So sort of tying the radio emission with phenomena that you observe at other wavelengths on the sun. So this is the experimental setup. At that time, it was an interferometric system working at 100 and 200 megahertz, two-element interferometer using Yagi antennas. I'd shown you the picture of the Yagi in the earlier slide. So on the top is the block diagram of the receiver for the system. And, I find it interesting that they have a monitor amplifier over here and a loudspeaker. And if you go through the paper, the reason for that is to identify radio frequency interference. So I find that interesting that from the very early days, in a relatively remote location like Chengalur, you still needed to take care of radio frequency interference. So it was a two-element interferometer, and in this middle panel over here, I'm showing you the fringes observed on the active sun using the system. Yeah.
There is a small little window on the right side. If you could just kill that on your screen. Maybe
oh, I'm so sorry.
Participants are, yeah. Thank you.
Is that better?
Yeah, it's fine.
Yeah. My apologies. Yeah. So the system, as I was saying, was also sensitive enough to detect scintillation from extragalactic sources. And I'm showing you a scintillation plot over here at the bottom. And that was another line of work which got started at that time. At the same, or shortly after that, a 20-foot parabola was also built to study, again, geomagnetic phenomena as well as scintillation studies of extragalactic sources. And it's interesting that this very early work, which had these two major themes, solar observations as well as observations of scintillating sources, are themes which continued to grow and develop in India over the next several decades, at Chengalur as well as in other places, as we will see. So radio astronomy at Kodaikanal, I'm sorry, I call that Chengalur, I beg your pardon, it's at Kodaikanal and other places over the next several decades. Radio astronomy at Kodaikanal continued, and I understand that these efforts were largely sort of Vainu Bapu's desire to continue to do cutting-edge radio astronomy. And I think CHV Shastri, who was hired around that time and making all of this, sort of putting all of this together and making the observations. So there was a 25 megahertz array, which consisted of two arms, each of which had 36 antennas, and that was operational from the late 60s. And it had fairly good spectral and time resolution for that time. It had four channel receiver, each of which had 100 kilohertz bandwidth and a 10 millisecond time constant. There was also a smaller cross dipole system for polarization observations. And the research themes, and I've shown you, examples of the data that were taken with the system. And these themes basically included observations of type 1 radio bursts, studies of the nature of the time and frequency structure of type 3 bursts, basically using, exploiting the frequency and time resolution of this instrument. And this work continued, I think, for close to a decade or so at Kodaikanal. Over the next decade, much larger arrays were built at Gauribidanur, and this is work which was done in collaboration with RRI, and we'll take a look at that at the moment. But before I leave Kodaikanal, what I'd like to say is that solar astronomy continued, if not with this array, with other instrumentation at Kodaikanal. There was been a continuous tradition of doing solar radio astronomy at Kodaikanal. And the latest in this sort of tradition is a wideband radio spectrograph, which has recently started taking data. And what this is showing you over here is a very high quality dynamic spectra of type 3 and type 2 radio bursts. And these are the kind of data that the spectrograph can just routinely take at Kodaikanal. All right, so with that, I'd like to move on to talking about developments at Gauribidanur. And the first large instrument which was built at Gauribidanur is on the outskirts, it's I think about a couple of hours journey away from Bangalore, was the first instrument built over there is what's called the GT, which is a large dipole array shaped like a T, operating at 345 megahertz. And this had a total of 1,000 dipoles. It's quite big. The east-west arm, which you can see more clearly over here, is 1.4 kilometers long. The south arm is about half a kilometer long, and it had a digital multi-beam forming system. So it's a joint project between IIA and the Raman Research Institute. This is about the time that V. Radhakrishnan, who's one of the pioneers globally of radio astronomy, joined RRI as its director and really began to build up both a group as well as a large amount of radio astronomy activity at RRI. So major studies with this array include imaging of the slowly varying sources in the solar corona, and I'm showing you some contour plots over here of data of images made with the GT. The circle that you see is the optical disk of the sun, and the contours are basically the observed radio emission from the solar corona. It also did a very wide area survey at 34.5 megahertz, and I'm showing you part of that over here. I think it was formed a good part of Dwarkanath's PhD thesis. And so this is an image of the Milky Way, showing you, various features in the radio, well-known features such as the North Polar Spur, Cassiopeia A, the disk of the Milky Way itself, all at observed at 34.5 megahertz. And there was also this very interesting observation, spectral line observation, looking for spectral lines from very, very large atoms. And so this is absorption produced from a carbon recombination line. The N over here is 575, so its Rydberg radius is of the order of 10 to the 5 angstrom. So we're really talking about giant atoms in space, which this telescope was sensitive enough to detect the absorption from, which then of course allows you to infer a number of interesting properties about the absorbing gas. There were several other instruments which came up at Gauribidanur. So there was Ramesh at IIA and his team, I think, were the people primarily associated with all of this. And what I'm showing you over here is a radio heliograph working from 40 to 150 megahertz, which has been operational since the late 90s. It's It's quite a large setup, 384 log periodic dipoles configured in 64 groups. The signal being processed by a 496-channel digital correlator, and is carried out a large number of studies of coronal mass ejections, coronal density gradients, and so on. So I'm showing you over here a radio image made by this heliograph in contours superposed on a coronagraph image of the sun, showing you the coronal mass ejection just starting up at that time. RRI also has actually conducted a number of innovative radio experiments at Gauri Bidnur. And I'm showing you first over here a prototype antenna which was built as a possible SKA prototype. So this is what called a preloaded parabolic dish. I think the idea was due to Govind Swarup, who was thinking of ways to build dishes without a whole lot of backup structure, and he came up with this. And Uday Shankar and others at RRI, working with Govind, fleshed out this idea completely and actually took it all the way to the prototype stage. Another experiment that I'd like to show you is this, which is called Zebra, or a zero spacing interferometer. So the idea over here was to try and detect the radio signal from, at very low radio frequencies. The interest in this is that at sufficiently low radio frequencies, you would expect to see spectral features because of what's happening to the neutral hydrogen at that time. So that H1 21 centimeter spectral line gets affected when you have the first energetic sources turn on in the universe, the epoch called the cosmic dawn. So the energy input from the cosmic dawn will start producing features in the H1 21 centimeter spectrum. This will be a global signal, that is, you expect it to be uniform across the sky. And so there's been a number of efforts aimed at detecting this experiment. And so this is one of them. And I'll spend a little bit of time talking about it. So the idea is that it's a global signal, and normally you cannot detect that with an interferometer because an interferometer detects the Fourier transform of the signal. And so if I have a global signal that it's uniform across the sky, it'll appear only as a DC, that is at zero spacing. So no interferometer would be sensitive to it. So what they've done over here is very clever. They've built a 50% reflecting screen so that each dipole that you see on the ground receives half the transmitted signal from the sky, and the other half is a reflected signal from the other half of the sky. And with everything properly managed, you would actually get a correlated component between these two components, which corresponds to the global sky signal. I'll come back to this global sky signal after a while. But I first want to move on to continue talking about low frequency arrays. RRI was also instrumental in setting up the 150 megahertz Mauritius radio telescope with Uday Shankar and his co-workers. I've showing you the picture over here, which it basically consists of 1,024 helical antennas in a 2 kilometer east-west arm, and then a number of antennas and trolleys in a north-south arm, which you could move to measure different components of the Fourier transform, and then therefore we make an image of the sky. So this telescope carried out a sky survey at 150 megahertz. I'm showing you an image from the sky survey over there. It detected 6,000 sources in the sky survey, as well as diffuse emission from the Milky Way. It's also used for pulsar studies and so on. The Raman Research Institute also made, very significant hardware contributions in the form of building digital receivers for the MWA array in Australia, and that's the array whose picture I'm showing you over here. It's located near Perth in Western Australia, and it's a precursor to the SKA, about which I'll say a little bit more shortly. The MWA is a very, very versatile instrument. It's carried out a very large number of projects, and I'm not going to try to summarize even what all it did. And work on low frequency arrays continues at RRI, and future projects that they have includes a proposed array which they call SWAN, which will sort of do VLBI, I understand, at low frequencies. I want to go back now to talking about detecting the signal from the cosmic dawn. So RRI actually built a series of instruments to probe the expected signal from the redshifted H1 21 centimeter emission or absorption from the epoch of formation of the first stars and active galactic nuclei, the cosmic dawn that I was referring to earlier. This basically Ravi Subramaniam, Uday Shankar and their collaborators. And I'm showing you here one of the latest versions of this instrument, which is called Saras, and which basically was floated on a lake. And the idea for floating it on the lake was to get under control the reflections that you would get from material below the antenna. If you put it on the ground, the reflections that you get from the ground are very hard to control. But on a flat, sort of fairly homogeneous body of water, it's much easier. It's much easier to control. So this is the instrument which recently published this result on the spectrum of the radio sky at low frequencies. And basically the spectrum they see is relatively flat, and that refutes the claimed detection earlier of an instrument called EDGES located in Western Australia. Before I leave radio developments at RRI, I'd like to talk about the millimeter wave astronomy at RRI. Again, this was an initiative by Radhakrishnan, also called RAD generally, and his colleagues and co-workers. A 10.4 meter millimeter wave telescope installed on the Bangalore campus in the late 80s. It had cryogenic receivers operating in the 3 millimeter band and carried out a number of observations, including observations of CO emission from molecular clouds, as well as SIO and methanol masers. It was, the first millimeter wave radio telescope in India. There have been further developments of high-frequency radio telescopes at RRI, including prototyping, a novel optical arrangement called Efficient Linear Imager by R. Balasubramaniam and his co-workers. But I think it would be fair to say that at least at the millimeter wavelengths, after the 10.4 meter telescope at RRI, there have not really been a great deal of development in India. That is changing, yeah.
5 minutes?
Yeah, that is changing a little bit now. ISRO is in the process of developing a sub-millimeter telescope operating at Hanle at the frequencies that I've given over here. At PRL, we had IPS activities also going on, principally at the array at Kaltej, which grew over time to a collecting area of 20,000 square meters, working at 103 megahertz, operating as a two-element interferometer. The scintillations were used to study the structure of radio sources, solar wind, ionic material, and the cometary tails, and so on. And this is work primarily led by Professors Arulkar and Bhosle, and I'm showing you over here, data which I think form part of Jerry Padmanabhan's thesis, showing you a number of interplanetary scintillation data for several sources. All right, I'd now like to move on to TIFR and the SKA. I don't have a whole lot of time, but I think it's a story many people are familiar with, so I can go fast. Radio astronomy at TIFR began with the Kalyan Radio Telescope in the late 1960s, built by Govind Swarup, who had returned to TIFR around that time, and working at 610 megahertz, and used some novel instrumentation, and was able to do interesting work on studying whether the solar radio emission at 610 megahertz shows limb brightening or not. But very shortly after that, the group moved on to build a really large radio telescope, the Ooty Radio Telescope, located in Ooty on a north-south hill slope with a slope of 11 degrees, which is the declination of that area, which basically means the telescope is equatorially mounted. So it's this giant telescope which can be rotated along its long axis, which remember is 0.5 kilometer long, to track sources in the sky. And it can point in the north-south direction by basically beam steering, electronically steering the beam, which is formed by addition of dipoles. The main science goal over here was to determine the radio source positions and sizes via lunar occultation. I think it would be fair to say that the Ooty Radio Telescope had a transformative impact on Indian radio astronomy. It did work on measurements of radio source angular sizes, on diffuse interstellar medium of the galaxy, both via studies of radio recombination lines and pulsars. studies of the heliosphere via scintillation of radio sources, as well as, interestingly, trying to study H1 at cosmological redshifts, as well as pulsars. It also trained a whole generation of radio astronomers and engineers, and is in use even today. I'm just going to flash through a bunch of results out of this, which basically illustrate the areas that I was talking about. After the UTI radio telescope, there was the UTI synthesis radio telescope, an array of small telescope around the UTI telescope to do synthesis imaging. It was operational only for a short period of time, and it made several images at 327 megahertz. But I think it also served this very useful purpose of being the training ground for building the next generation synthesis radio telescope, the JMRT. So the JMRT is an array of 30 antennas, each of which is 45 meters in diameter, using a very novel antenna design come up by Govind Swarup, which made the whole thing very reasonably priced. Its main science goals were studies of H1 at high redshifts, pulsars, radio galaxies, and so on. It's been in regular operations from 2001. It's a very versatile telescope. It's most sensitive in the world in some of its operating frequencies. And the other interesting thing is that it was designed from the very start to work in both the imaging mode and the array mode. That is, it can have digital backends which both allow you to make images of the sky, as well as to do beamforming, to do very high time resolution pulsar observations. And it was one of the very first arrays to enable both of these modes of operation. So the JMRT Classic is what I've called it, the thing which was inaugurated in 2001, had 5 frequency bands and operated with a relatively narrow bandwidth of 32 megahertz. It carried out a very wide range of studies, ranging from H1 21 centimeter from the epoch of reionization to studies of scintillation caused by CMEs in the sun over this entire range of distances, over the range of scales from diffuse gas and clusters of galaxies to pulsars. And again, I'm obviously not going to try over here to summarize the science done. What I would like to move on to is the upgraded JMRT, which was released in 2019, which is, for all purposes, effectively a new telescope, offering nearly seamless frequency coverage from 30 to 1500 megahertz, with an increase in instantaneous bandwidth to 400 megahertz, which very significantly improves the sensitivity as well as the image fidelity. And the power of the UJMRT is amply demonstrated by a slew of new publications, recent publications, which again, I won't try and summarize. And, there have been several talks at this ASI, indeed using UJMRT data. And, so the story doesn't end here. Explorations for further expansions of the JMRT, currently dubbed the eJMRT, are underway at the moment. I'll skip this bit about observing with the JMRT, and I'll just move on to the square kilometer array, which is the next generation global mega radio telescope, which is eventually planned to have the collecting area of 1 square kilometer, be located at 2 sites in South Africa and Australia, and operate over a wide range of frequencies. There's been a workshop on SKA at this ASI. So again, most people I'm sure have heard about it. So I'll just give a status. So it's being built in a phased manner. And what is coming first is the SKA phase 1, for which the design is completed and which commissioning and construction is expected to start shortly and complete by 2027, with early science starting shortly before that. So where is India in the SKA? There is the SKA India Consortium, which has more than 20 institutional members, and the map shows you where they are. And these basically coordinate the contribution to the SKA, technical contributions that we are making to the SKA, as well as start preparing to do science with the SKA. So what is the status right now? The current planning is for India to contribute at a 67% to the SKA phase 1. We are the lead country to build the telescope manager, which where NCRA is playing a major role. It's also part of SKA low digital signal processing package and a number of other packages which I've listed over here, and I won't walk through given the time. In addition, it's planned to have an SKA regional data center in India, which would house a good fraction of the SKA data, particularly that relevant to teams from India. There's also a significant human resource development program that is proposed. And the final proposal for participation in SKA1 is in the final stages of review by the Government of India. So I think that's all I had. Thank you.
Thank you very much, Jairam. So online participants, you can type your questions in the chat box. Let me see if I have raised hand in the, yes, there is one question here.
I was just interested to see if there were any thoughts of expanding to the space VLBI.
Jairam, you heard the question?
There was a question about space VLBI.
That's correct. Yeah.
I'm not aware of any, there has been some exploratory work in space VLBI, but I'm not aware currently of an active proposal. I mean, if there is one, somebody should please correct me. Yeah, so that is my understanding, that there has been some discussions about it, but I don't think there's anything active right now. There is a proposal ongoing from, to continue this cosmic dawn experiments from space, but I'm not aware of anything about space VLBI.
Any other questions from offline participants first? Yeah, Nirupam had a question. One quick comment. Weber was the first to publish 1944, but not the first to observe radio emission from the sun.
That's correct.
After and southward. So that's a comment more.
No, that is correct. I was just picking from published work, but thank you, Nirupam.
Neeraj also pointed out that RRI also contributed to digital hardware for the UTR-2 radio telescope in Ukraine around the year 2000.
Thank you, Neeraj.
Shanmugam Balan, can I ask a question? Can you unmute Shanmugam Balan? Can you just unmute?
Hello, can you hear me?
Yeah, go ahead.
Thank you, Dr. Jairam, for your amazing talk. So my question was that once we're moving to very large radio telescopic arrays right now. So like this SK, for example.
Dipankar, I could not hear that at all, unfortunately.
Yeah, we could hear him. Can you go ahead again, Shanmugam? I will try to repeat the question. Just go ahead.
Okay, sure. So my question was that we're moving to extremely large radio telescopic arrays. So like SWAN, for example, is across India, and the SK telescope is there in South Africa and Australia. So the thing is, there's like extremely different weather in like these different regions. So how exactly is this handled? Is the data like partially only observed, or is there some sort of modification which you can make to the data so that collection can be handled even during adverse weather conditions?
Could you hear, Jairam, the question?
No, I could not. Could you please repeat it?
Yeah, so what he is referring to, there are these major facilities, SK, and different parts of the globe with varied weather conditions. So whether any thought is there how to mitigate those different adverse weather conditions in terms of data processing and so on.
I'll come back to that in a moment. But I just wanted to go first to that question about space VLBI, where I did want to mention that the Russians, of course, have launched a satellite to do space VLBI, radio astronomy, I think, where the 327 megahertz part of that system was built, the receiver was built by India. And supplied by India, and I think we've also provided some ground support for those observations. So I just wanted to, for completeness, mention that about space VLBI. And yes, to get back to this question, so certainly both of these facilities which are coming up are in very hot, dry, arid regions. And obviously one would have to take due care when sort of building the instrumentation over there and to handle all of this. But I'm not really that familiar with exactly what is being planned to mitigate high temperatures and so on. The instrumentation, of course, much of it which sits out in the field will just have to deal with it.
Thank you, Jairam. I think I would like to thank